Welcome to the Deep Dive. Today we're jumping straight into something generating a lot of buzz in the AI world. LLaMA, that's LLaMA, a new collection of large language models from Meta AI.
Yeah, there's definitely been a lot of talk about this one.
For you following the rapid advancements in this field, this is one to pay attention to.
Absolutely. This isn't just another addition to the ever-growing list of language models. The research community is particularly excited about Llama's unique approach.
Exactly. And that's precisely what we're going to explore today. Our mission really is to understand what makes LLaMA stand out, particularly its focus on being both efficient and, well, openly trained.
Right. That openness is key.
Our primary source for this deep dive is the research paper itself, titled LLaMA, Open and Efficient Foundation Language Models. So let's get right into it.
Okay. Let's start with a core concept that Llama really emphasizes: achieving high performance with smaller models by training them on just a massive amount of data.
Right.
You see, for a while, the prevailing wisdom was that bigger models, more parameters, would inherently be better.
It felt like an arms race, almost. Who could build the biggest? But the paper references some interesting work, I think, from 2022.
Yeah, Hoffman et al.
Right, that started to question that assumption, suggesting that for a given amount of computing power, you might actually get more bang for your buck with a slightly smaller model fed a much larger data set.
And what's fascinating here is how Llama takes that idea and specifically optimizes for what they call the inference budget.
Inference budget, okay, so that's the cost and speed of actually using the model once it's trained, right?
Yeah.
As opposed to the huge resources for the initial training.
Exactly.
So for someone thinking about practical applications, this is about real-world usability.
Precisely. And this is a critical distinction. While a, gigantic model might reach a certain performance level faster during initial training, Llama's research indicates that a smaller model, trained more extensively on more data, can ultimately be more efficient and faster when you're actually deploying it.
Huh. It almost flips the script, doesn't it?
Yeah.
Smaller actually outperforming larger in practical terms.
Yeah.
The paper even points out that their 7 billion parameter model continued to improve even after processing a trillion tokens of data, way beyond what was thought to be the sweet spot for a 10 billion parameter model.
And that's truly groundbreaking. It suggests a potential, a paradigm shift. For a long time, the industry chased ever larger models. LLaMA's success suggests clever training strategies, and the right data might be more impactful than just scaling up parameters.
Which has huge implications for who can actually use this tech.
Absolutely.
So what kind of performance are we actually seeing from these LLaMA models? They come in different sizes, right?
Yes, they've released a range from a relatively compact 7 billion parameters up to a pretty substantial 65 billion. And the results they've achieved on standard AI benchmarks are quite remarkable.
Give us some of the highlights. What really stands out?
Well, the paper makes the striking claim that their 13 billion parameter LLaMA 13B, actually outperforms GPT-3.
GPT-3, the 175 billion parameter one.
The very same. Outperforms it on most benchmarks. Think about that for a moment. A model more than 10 times smaller, getting better results on a wide range of tests.
That's incredible. A real David versus Goliath story in AI.
It really is.
And what about their largest model, the 65 billion parameter LLaMA? How does that stack up against the current top contenders?
They report that the 65B version is competitive with the best models available, like Chinchilla-70B and PaLM-540B. These are some of the heavy hitters.
So competitive with the absolute state-of-the-art.
Pretty much, yeah.
This has significant implications for accessibility, doesn't it? A smaller model achieving performance like that.
Absolutely. I mean, the fact that the LLaMA 13B model can even run on a single high-end consumer graphics card, that's a potential game changer.
Right.
It could democratize access to really advanced AI capabilities, putting tools that were previously just in massive research labs into the hands of, a much broader audience.
Okay, so efficiency is a huge part of the story. But the name LLaMA also points to open. What about the training data?
This is another crucial differentiator. LLaMA was trained, and they emphasize this exclusively on datasets that are publicly available.
That's a big deal, isn't it?
Yeah.
Compared to some other big models where we hear about proprietary datasets, massive book collections, social media stuff.
Exactly. Things where the exact sources and composition aren't always fully transparent. Models like Chinchilla, PaLM, GPT-3 rely on substantial amounts of data that isn't publicly accessible or, fully documented.
Okay.
And while there have been other open source language model projects, they mention OPT, GPT-NeoX, Bloom, GLM.
Right, I've heard of those.
LLaMA, at the time of this paper, really achieved performance levels competitive with those top proprietary models, which those other open efforts hadn't quite reached yet.
So using only public data, but still hitting that top-tier performance. What's the key advantage there for researchers or for people just following this?
Well, the significance really lies in transparency and potentially faster progress. If the training data is public, other researchers can more easily understand how it was trained, maybe replicate the results, identify limitations, build upon the work.
Makes sense. It fosters a more open environment.
Exactly. More collaborative.
Okay, so smaller models, open data. Now, what about the technical side? Any specific architectural choices or training techniques that help them get this performance?
Yes, absolutely. While the basic architecture is still the transformer, which is pretty standard now.
Yeah, Vaswani et al.
Right. The LLaMA team incorporated several key modifications, drawing inspiration from recent advancements.
What kind of tweaks? Give us the sort of non-expert rundown.
Certainly, one important change is pre-normalization, which they got from GPT-3. Think of it like adjusting the signals before each processing step, not after. It helps stabilize the training, especially with these really deep networks.
Okay, training stability sounds vital for these huge models. What else?
They also use the SWAGL activation function. PaLM used it too, but LLaMA used a slightly different configuration. Activation functions are basically how the model learns complex patterns. SWAGL seems to help performance on certain tasks.
So different ways the model processes information internally. Anything else in the architecture?
Yes, they used rotary embeddings, or ROPE. That came from GPT-Neo. Instead of telling the model the absolute position of each word, like word 1, word 2, word 3, ROPE encodes the relative positions, how far apart words are.
Ah, so it's more about relationships between words.
Exactly. And that can be really effective when dealing with longer sequences of text.
Interesting. Okay, let's talk more about that data. We know it's public, but what exactly did they train on?
It's a really diverse mix. The
Hmm.
biggest chunk, a massive 67%, comes from English Common Crawl.
Common Crawl, that's the huge scrape of the web, right?
Precisely. They used 5 different snapshots from 2017 to 2020, and they processed it heavily using a pipeline called CCNet.
What did CCNet do?
Things like deduplication, language identification to filter out non-English pages, trying to filter low-quality content using language models. They even had a system to prioritize pages that were used as references in Wikipedia.
Huh, that's clever. Trying to get higher quality web data.
What else? Another 15% came from C4, also derived from Common Crawl, but with different pre-processing and quality filtering rules. Then 4.5% from a public GitHub dataset.
Good.
Yep, code, focused on projects with open source licenses like Apache, BSD, MIT. They filtered that too based on line length, alphanumeric ratio, trying to exclude short or maybe machine-generated stuff.
Makes sense. Focusing on real, openly licensed code. What about more traditional text like books or encyclopedias?
Right, 4.5% from Wikipedia, covering 20 languages using Latin or Cyrillic scripts. They cleaned that up, removed hyperlinks, comments, etc. Another 4.5% came from Books public domain stuff from Gutenberg Project, and also the Books 3 part of the PILE dataset.
The pile, okay.
Yeah, it's a big collection. And they even deduplicated at the book level to avoid training on the same book multiple times if it appeared in both sources.
Good mix. Web beta, code, reference material, literature. Anything else?
Yep, 2.5% from ArcZIF, the scientific paper preprint repository. They processed the LaTeX source files, tried to extract the main text, remove bibliographies, comments, expand macros.
Wow, processing latex, that's involved.
It is. And finally, 2% from Stack Exchange, popular Q&A site. They took the top 28 most active sites, removed HTML tags, and sorted answers by score to prioritize the better ones.
That is quite a data set. Comprehensive and diverse.
All right.
And they use byte pair encoding, BPE, for tokenization.
Yes, with sentence piece, it splits words into smaller subword units, handles unknown characters using bytes, useful for this wide range of text and code.
And this all added up to?
About 1.4 trillion tokens in total, a massive amount of training data. For most of it, each token was only seen once during training. Wikipedia and books were exceptions. They cycled through those about twice.
Okay. Now, training something this big obviously needs immense computing power. What can you tell us about the actual training process itself?
Well, they use the Atom W optimizer, pretty standard for these big models. They carefully tuned the hyperparameters, the settings controlling the learning.
Right.
They used a cosine learning rate schedule, gradually reducing the rate over time. Also, weight decay and gradient clipping to help keep training stable. And a warm-up period at the start where the learning rate increases gradually.
Sounds very carefully managed. And to handle the sheer scale, the model size, the data, they must have used some advanced implementation tricks.
Absolutely. Several key optimizations to speed things up and save memory. A big one was an efficient implementation of causal multi-head attention.
Attention, that's core to transformers.
Exactly. Without getting too technical, this optimization avoids storing all the intermediate calculations, saving memory and computation time. They used a library called XFormers for this, based on recent research.
Okay, optimizing attention sounds like a major win. What else?
They also use activation checkpointing. Think of it like strategically saving snapshots during the forward pass and then recomputing parts during the backward pass instead of storing everything. They even manually optimize the backward function for the transform layers to maximize this benefit.
Clever ways to manage the huge memory demands and distributing it across machines.
Yep. They use both model parallelism, splitting the model itself across GPUs, and sequence parallelism, splitting the input data sequence across GPUs. And they overlap the computation with the communication between GPUs to minimize delays.
A whole suite of techniques.
Yeah.
The paper even gives an example for the 65B model, right? The scale of resources.
That's correct. They mention using 2048 high-end GPUs. Their code could process a significant number of tokens per second per GPU. Training the 1.4 trillion tokens for the 65B model took approximately 21 days.
21 days on over 2,000 GPUs. Just staggering.
It really gives you a sense of the scale.
Okay, so they've built these models, trained them on this vast data set. How do they actually perform? How do they test them?
They evaluated LLaMA extensively on a wide range of standard benchmarks, looking at both zero-shot and few-shot learning.
Quick reminder, zero-shot is.
Zero-shot. Give the model a task description and a test example, no prior examples of that specific task.
And few-shot.
Few-shot. Give it a small number of examples of the task first, then the test question, kind of like priming it.
Got it. So how did LLaMA do on tasks needing common sense reasoning?
They tested on 8 different common sense benchmarks. Things like true-false questions, predicting the next event, resolving ambiguous pronouns. Across these, the LLaMA 65B model generally performed very well, often outperforming models like Chinchilla-70B and PaLM-540B on many tests.
Even the big ones.
Even the big ones. And notably, the much smaller LLaMA 13B consistently outperformed the significantly larger GPT-3 on the majority of these common sense tasks.
But that pattern keeps repeating. Impressive.
Mm-hmm.
What about directly answering questions, like question answering?
They looked at datasets like natural questions and trivia QA in a closed book, setting no external web searches allowed for the model. On both of these challenging benchmarks, LLaMA 65B achieved state-of-the-art results in both zero-shot and few-shot scenarios. And again, LLaMA 13B showed competitive results compared to GPT-3 and Chinchilla despite being much smaller.
So reasoning, question answering. What about understanding text more deeply, like reading comprehension?
They use the RACE benchmark for that. It's based on English reading comprehension exams for middle and high school students. Here, LLaMA 65B performed comparably to PaLM-540B, and LLaMA 13B, once again, outperformed GPT-3.
Okay, so it's not just retrieving facts. It seems to grasp the meaning. What about specialized areas? Math, code generation.
This is where it gets particularly interesting. On mathematical reasoning tasks using the Math and GSM-8K datasets, LLaMA 65B actually outperformed Minerva 62B on GSM-8K.
Minerva, wasn't that specifically fine-tuned for math?
Exactly. Minerva is a PaLM model fine-tuned on a large corpus of math data. LLaMA was not specifically tuned for math, yet it outperformed Minerva on that benchmark.
That's a really significant result for a general model.
It really is.
And code generation.
They tested on human evil and MBPP benchmarks. For models with similar parameter counts, LLaMA outperformed other general models like LaMDA and PaLM, which weren't code fine-tuned. In fact, the 13 billion parameter LLaMA even surpassed the much larger 137 billion parameter LaMDA on both code benchmarks.
Wow.
Now, they do note that models specifically fine-tuned for code can do even better, but still, it shows LLaMA's strong general capabilities extend well into code generation.
It sounds remarkably versatile. Performing well across such a diverse set of tasks, often beating much bigger models. Was there any area where it maybe didn't quite match the very top models?
Yes, one area they highlight is the Massive Multitask Language Understanding Benchmark, or MMLU. It covers a very broad range of subjects.
Okay, how did it do there?
On MMLU, the LLaMA 65B model lagged a bit behind Chinchilla-70B and PaLM-540B. Still very strong performance, but not quite at the level of those larger models on this particular very broad test.
Any speculation why?
The paper suggests a potential reason might be the composition of their training data. While diverse, it might have had comparatively less data from books and academic papers compared to the datasets used for Chinchilla and PaLM, which reportedly used terabytes of book data. They note that another model, Gopher, outperformed GPT-3 on MMLU, possibly due to its larger proportion of book data.
Ah, so the specific mix of training data still matters significantly, even with massive scale.
Absolutely. The details of the data diet seem crucial for performance on certain types of benchmarks, like broad academic knowledge.
Now, the paper does touch briefly on fine-tuning LLaMA, specifically for instructions, right? LLaMA AI.
Yes, they did experiment with that. They took the 65B model and did some additional fine-tuning on an instruction dataset, similar to other recent work. They called this version LLaMA AI.
And what happened when they did that?
They saw significant and rapid improvements, particularly on that MMLU benchmark we just discussed.
Ah, so instruction tuning helped close that gap.
It seemed to. LLaMA AI outperformed other instruction-tuned models of comparable size, like OPT-IML and FLAN-T5-XXL. It suggests even a modest amount of instruction tuning can really boost a model's ability to follow directions and perform well across diverse tasks. Still not quite matching the absolute best, like GPT Code DaVinci 002 at the time, but a big improvement.
Okay, so base LLaMA is strong, and instruction-tuned LLaMA AI is even better at following directions. Now, a critical aspect with any large language model is, well, the potential downsides. Bias, toxicity, misinformation. Did they evaluate LLaMA on these fronts?
Yes, they did. They acknowledged the importance of assessing potential harms. They used several standard benchmarks for this.
What did they find regarding toxicity?
They used the real toxicity prompts benchmark. Interestingly, they found that toxicity tended to increase with model size, which has been observed before. It was particularly noticeable for prompts designed to be respectful. The model sometimes generated more toxic responses to those. They do note some methodological differences compared to other studies, though.
Bigger models potentially being more toxic.
Yeah.
That's concerning. What about other biases like gender or religion?
They used the Crow-S pairs benchmark to look at biases across various categories, gender, religion, race, etc. They compared LLaMA with GPT-3 and OPT-175B. On average, LLaMA 65B showed slightly less bias according to this metric, but it did exhibit higher bias specifically in the religion category compared to the others.
So a mixed picture on bias. Any other tests?
They also used the Wino gender benchmark, which focuses on co-reference resolution and potential gender bias. LLaMA performed better when pronouns like their, them, someone were used, which might indicate less bias in those cases. However, its accuracy dropped on gotcha examples where the occupation stereotypically associated with one gender was paired with a pronoun of another gender.
Suggesting it might still rely on some ingrained gender stereotypes from the training data.
Potentially, yes. And finally, they looked at truthfulness using the Truthful QA benchmark, which measures a model's tendency to generate common misconceptions.
How did LLaMA do there? Is it spitting out falsehoods?
LLaMA models actually scored higher than GPT-3 in generating answers categorized as both truthful and informative. However, the overall accuracy on this benchmark was still quite low for all models tested, indicating that hallucinations or generating factually incorrect information remain a significant challenge.
Right, so better than some predecessors on truthfulness, but still far from perfect. Hallucinations are definitely still a big issue.
A very big issue across the field.
Okay, one more practical consideration. The environmental impact. Training these models takes enormous energy. Did they report on the carbon footprint?
Yes, they included estimations in the paper. They calculated the power consumption during training based on GPU hours, estimated power usage, data center efficiency PUE, and the carbon intensity of the U.S. power grid.
And how did LLaMA stack up?
For example, training the largest 65B model was estimated to consume around 539 megawatt hours and result in about 237 tons of CO2 equivalent emissions. They provided comparisons to OPT-175B and BLOM-175B, which, being larger models, had significantly higher estimated footprints.
So, while still substantial, LLaMA's efficiency focus does translate to a lower environmental cost compared to training some of those even larger models.
Exactly. And they express hope that by releasing these more efficient models, it might actually help reduce future training emissions, as researchers might not need to train their own massive models from scratch as often.
That's a good point. Releasing efficient, capable models could prevent redundant training efforts.
That seems to be part of the motivation.
Okay, the paper also includes a brief overview of related work, placing LLaMA in context.
Yes, they give a quick history from early underground statistical models up to modern neural networks. They mention key milestones like BERT, GPT-2, GPT-3, and the whole study of scaling laws, how model size, data size, and performance relate.
Right, connecting back to that core idea of LLaMA challenging the simple bigger is better scaling law.
Exactly. It positions LLaMA's focus on efficiency and optimizing training compute as a significant step in that ongoing evolution of language model development.
So wrapping things up, the key takeaways for LLaMA seem to be its impressive efficiency, achieving top-tier performance with smaller models.
It's training exclusively on publicly available data, which is huge for transparency and reproducibility.
And its strong performance across a really wide range of benchmarks, often beating much larger models.
Right. Combined, these make it a really noteworthy advancement, especially with Meta making the models available to the research community.
It definitely feels like it lowers the barrier to entry for working with truly powerful language models.
It certainly has that potential, accelerating research and broadening participation. Though, as the evaluation showed, challenges around bias, toxicity, and truthfulness remain critical areas for ongoing research.
Absolutely, the work is far from over on those fronts.
Indeed.
So, as we conclude this deep dive into LLaMA, it leaves us with a thought-provoking question, perhaps for you listening. Considering this trend towards more efficient and openly available AI models like LLaMA, what new possibilities, what new applications might emerge as this kind of power becomes more widely accessible?
Yeah. What happens when these tools are not just in a few big labs?
Exactly. It definitely feels like we're on the cusp of some significant changes in the AI landscape. Thanks for joining me for this deep dive.
My pleasure. Lots to think about.
Until next time.